I'd like to talk with you about what do sacrificial bonds and hidden length have to do with bone fracture risk. Now, sacrificial bonds and hidden length is a really exciting scientific concept that I was lucky enough to develop together with Galen Stuckey and Dan Morse at the University of California. We first discovered this amazing phenomenon that's responsible for the toughness of many natural materials in abalone shells. Now, an abalone shell is 97% crystalline calcium carbonate, but it's 3,000 times more fracture resistant than crystalline calcium carbonate. And so you ask yourself, how can that be? How can you add 3% of organic to something and make it 3,000 times more fracture resistant? I mean, imagine you could do that with concrete. Imagine you could go to Home Depot and buy a bottle of something that you would put in at 3% into your wheelbarrow of concrete, and it would make your concrete 3,000 times more fracture resistant. I mean, wouldn't that be an amazing thing? So we wanted to see, how is it that nature did that? How did nature put in 3% of organic in this thing and make it 3,000 times more fracture resistant? Now, in order to uncover this mystery, it required the atomic force microscope, pulling on molecules. What happens in this case is that the atomic force microscope has a lever, and this lever can go down to a surface and stick to a molecule and pull it up from the surface. Now, there's a laser that bounces off the back of the cantilever onto a photodetector, and so if that cantilever bends because the molecule's pulling on it, you can detect that by the motion of the light spot on the photodetector. And so with that, we can measure the force, and we combine that with a measurement of the distance from the surface, and we get graphs like the one shown there. What you can see happened in these curves is the force went up and then dropped. It went up and then dropped. And then we did it again, and it would do the same thing, not exactly the same pattern. It had the same idea of going up and then dropping, up and then dropping, up and then dropping, but it wasn't exactly the same. And then we did it again. It shows 3 times there. So what in the heck is going on that when you're pulling on a molecule, the force goes up and then drops, and it does this repeated pattern? This is the phenomenon of sacrificial bonds and hidden length. The idea is the abalone shell is made up of all these little plates of mineral, and the plates are about the thickness of an optical wavelength, which is why you get these interference colors bouncing off the plates. And what the adhesive needs to do is to stick all these plates together. And so you imagine some organic molecule being used as an adhesive. If it was really, really short tether, then as soon as the plates were pulled apart a little, they would break apart and you'd be done. On the other hand, if you use, like, say, my hands or the plates, if you use a really long molecule between them, then the problem is there's no restoring force to hold the plates together until the plates get quite far separated. So you'd like the advantage of a short coupling so that you had force from the beginning, but you'd like to have a long polymer so that it would keep resisting far out. So nature's trick for doing that is sacrificial bonds and hidden length. What nature does is it takes the long polymer adhesives, which in the case of nature are proteins, and puts side groups on them that can bind to each other or bind to other molecules in solution. So it's like what they'll do is they'll hide some of the length of this from the ends by tying up some of the length, and we call this hidden length. So we call these sacrificial bonds. We call them sacrificial bonds because they sacrifice themselves. They break before the backbone of the polymer breaks. If the backbone of the polymer breaks, you're done. But these bonds can reform. And so what happens is, as the plates start to separate, at first it's like it's a short chain. And so it gives restoring force right away. But then as you pull further and further, the force goes up, 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 and then a sacrificial bond breaks. Then the force drops. See, the force is now low again. You stretch further and further, the force goes up, 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 until a sacrificial bond breaks. And again, force goes up, 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 until sacrificial bond breaks. And so it fights you all the way out. And this is the principle of sacrificial bonds and hidden length. And this is why the abalone shell is 3,000 times more fracture resistant. It's the geometry coupled with this amazing mechanism that nature has invented. Now, abalone shell fracture is not much of a human problem, right? I mean, some people might have abalone shells lining their walkway that they wouldn't want to be cracked, but it's not really a problem for humans how easily abalone shells fracture. But for humans, the important biomineral is bone. Is bone fracture important? Well, yes, of course. Bone fracture is very important for humans. And so we wondered, does this same mechanism exist in bone as exists in abalone shells? And so we took bone and we tried the same experiment on bone. And you see, indeed, there are the sacrificial bonds and hidden length in bone. It has the same phenomenon. The force goes up and then drops, up and then drops, up and then drops. In this particular slide, we were studying things like how long you wait between pulls. Like the top one, we had waited just 1 second until we pulled again, and the bottom one, we waited 100 seconds. See, because the beauty of this phenomenon is that once the force goes away, these bonds, the sacrificial bonds, can reform. And so what happens is there's something called entropic elasticity that makes polymers want to come back on themselves, and so it does. And you know, it gets mushed around like this in nature for times of order there, 10 seconds, 100 seconds. It gets mushed around. This demo does not always work, but let's hope. Perfect. All right. So bonds reformed. Now, if I pull this, it's not going to be exactly the same as the first time, right? The bonds, it's a different configuration of bonds, but it's the same principle. The force goes up and then drops, up and then drops, up and then drops. That's why the curves aren't all the same. You know, it's just because these bonds form kind of at random, but they fulfill the purpose of making it difficult to fracture the bone. And so sacrificial bonds and hidden length do exist in bone. We believe that they're important for bone fracture risk, that they make bone more resistant to fracture. And now, with the advent of reference point indentation, it's going to be possible to check out what can be done to improve sacrificial bonds and hidden length to prevent bone fracture. I think this is an exciting new opportunity that can hopefully help maintain active life for elderly people.